Your computer is lying to you. Not loudly, not maliciously, calmly, politely, with perfect timing. Every time you tap a key, click a button, or open an app, your machine gives you a comforting promise. I did exactly what you asked. Instantly, correctly. But that promise is fake, and it has to be. Because if your computer actually followed the most basic rule we're taught about logic, rules, and correctness, it would feel unbearably slow, almost unusable. So instead, modern computers cheat. They guess. They skip steps. They pretend work is finished before it actually is. They act confident first and apologize later. And here's the uncomfortable part. This isn't a rare bug or a design flaw. It's the core survival strategy of every fast system you use. Phones, laptops, servers, even the apps handling your money. Speed today exists because computers routinely break a rule they're never supposed to break. A rule we trust with our data, our decisions, our reality. So what is that rule? When did machines start breaking it? And what happens the day the lie stops being harmless? That's where this story actually begins. For most of computing history, speed was not the goal. Correctness was. Early computers were slow, expensive, and painfully literal. They followed a simple moral code. Do one thing at a time, in order, and never move on until you are absolutely sure the last step is finished. No guessing, no shortcuts, no assumptions. This rule had many names depending on who you asked. Determinism, sequential execution, strict consistency. But the idea was simple enough to explain to a human. A machine should never claim something is done unless it actually is. That rule worked fine when computers filled rooms and processed payroll overnight. It worked when one program ran at a time. It worked when users were patient and expectations were low. Then everything changed. By the late 1980s and early 1990s, computers got faster, but humans got faster too. We stopped submitting jobs and waiting. We started clicking, typing, dragging, interrupting. We expected instant feedback, even when the machine was juggling dozens of tasks underneath. And here's the problem. No one likes to say out loud, real correctness is slow. Memory takes time to respond. Disks are glacial compared to processors. Networks introduce delays measured in eternity, at least by a CPU standards. If a computer waited for absolute certainty at every step, it would spend most of its life frozen, politely waiting for confirmation. So engineers made a choice. They didn't officially abandon the rule. That would sound reckless. Instead, they bent it, quietly, reasonably, one small exception at a time. What if the computer assumed a piece of data would be there by the time it needed it? What if it acted like an instruction finished, even though it was still in progress? What if it guessed which path a program would take and prepared the result in advance? At first, these were tiny optimizations. Invisible, safe, almost boring. But layer by layer, decade by decade, modern computers evolved into systems that run on confidence instead of certainty. They move forward on predictions. They clean up mistakes later. They break the old rule constantly because following it would mean falling behind. And today, that trade-off matters more than ever. Because now computers don't just display text or crunch numbers. They decide which transactions go through, which messages arrive first, which actions feel instant, and which feel broken. And all of that speed rests on a quiet agreement. We'll accept being wrong occasionally as long as it feels fast. Here's where the rule really starts to crack. Inside your computer, nothing actually happens in a clean, single-file line anymore. Instructions pile up. They overlap, they race each other, and the machine doesn't wait to see how things turn out. It places bets. Take a modern processor. It can execute billions of instructions per second, but it's constantly blocked by slow parts of the system. Memory, storage, network. If it waited patiently every time, most of that expensive silicon would sit idle doing nothing. So instead, the processor predicts the future, literally. It looks at your program and says, based on the last 1,000 times that you're probably going to do this next. Then it starts doing that work before it knows for sure. This is called speculative execution, but the name makes it sound more cautious than it really is. It's not speculation, it's confidence bordering on arrogance. If the guess is right, everything feels instant. The lie becomes invisible. If the guess is wrong, the computer quietly erases the evidence and rewinds, pretending it never happened. Most of the time, no one notices. The same trick shows up everywhere. Your operating system tells an app that data is written, even though it's still sitting in a cache, waiting its turn. Your phone shows a message as sent while it's still negotiating with a server halfway across the planet. Databases confirm transactions optimistically, assuming conflicts will be rare and fixable later. These systems don't wait for truth. They assume it, and the math encourages this behavior. If you're right 99.9% of the time, the speed gain dwarfs the cost of the occasional rollback. Users feel smoothness, not correctness. Latency hurts more than rare mistakes, so engineers optimize for the thing humans notice. But there's a catch that grows with scale. The more predictions you stack on top of each other, the harder it becomes to fully undo a wrong guess. Some effects can't be cleanly erased, some information leaks, some assumptions escape into places they were never meant to go. That's how theoretical shortcuts turn into real-world problems. This is how performance hacks become security vulnerabilities, how minor inconsistencies turn into system-wide failures, how computers start behaving in ways that are technically allowed, but deeply unsettling. And once the system is fast enough, nobody wants to slow it down again. The turning point came when the lies stopped being local. For years, the damage was contained. A wrong guess meant a redo. A delayed right meant a brief pause. The system cleaned up after itself and moved on. Engineers told themselves the rule was technically still intact. Nothing bad persisted. Then researchers started asking uncomfortable questions. What if the computer guessed wrong and something escaped before the rewind? What if a temporary assumption left a permanent trace? In 2018, the industry got its answer. Security researchers revealed that speculative execution, the same trick that made computers feel magically fast, could be abused to read data that should have been completely inaccessible. Passwords, encryption keys, private memory. Not by breaking locks, but by watching the shadows left behind by guesses that were never supposed to count. The computer followed the rules and broke them at the same time. From the machine's point of view, nothing incorrect happened. The incorrect path was rolled back, officially erased, but the physical side effects, tiny changes in timing, cache state, heat, remained. And with the right patience, those side effects told a story. Suddenly, the lie was no longer harmless. Fixing it wasn't simple. You can't just turn off speculation without gutting performance. Some patches slowed systems down by double digits overnight. Cloud providers paid the price in power and money. Everyone else paid it in silence, with machines that were slightly slower and a little less honest about why. And this wasn't an isolated case, it was a pattern. The same rule-breaking shows up in distributed systems that disagree about reality for a few milliseconds, in financial platforms that assume trades won't collide, in social feeds that optimistically reorder truth, in AI systems that return confident answers before fully checking their work. Speed won. Again. What we learned in that moment was not that computers were flawed, it was that modern computing is built on a negotiated relationship with truth. Accuracy is deferred. Consistency is conditional. Correctness is something we converge on later if needed. The system works because most of the time, the world behaves nicely. But when it doesn't, the cracks are no longer theoretical. They're systemic. So here's the rule: the computers break all the time to stay fast. They move forward before they're allowed to be certain. They assume the future will behave. They reward confidence over patience. They treat truth as something to clean up later. And to be fair, it works. Most of the time. Your apps feel instant because they're lying on your behalf. Your operating system feels smooth because it delays reality until you demand it. The internet feels responsive because thousands of machines agree to be temporarily wrong together. But this is not a free trade. The faster we demand systems to be, the more we encourage them to guess. The more they guess, the harder it becomes to reason about failure. When things go wrong, they don't fail loudly. They fail subtly, inconsistently, in ways that are hard to reproduce and easy to dismiss. That's why modern outages feel strange. Why bugs vanish when you try to debug them. Why security flaws exist without a single line of bad code. The system didn't break. It behaved exactly as designed, under assumptions that quietly stopped being true. And this matters now more than ever, because we're handing these fast, optimistic machines more responsibility. Money movement, infrastructure control, medical decisions, automated judgment. Systems where "we'll fix it later" is not always an acceptable answer. The uncomfortable question isn't whether computers should be faster. It's whether we still remember which rules they're breaking to get there. Because once speed becomes the baseline, slowness looks like failure. And correctness starts to feel optional. So the next time something feels instant, ask yourself, what had to be assumed for that speed to exist? And what happens the day the assumption is wrong?